So as we were doing before with the hypothesis testing on 1 and 2 samples, we want to know if this correlation between these two variables is significant. So we're going to use two things. We're going to use the R value that we have calculated and the size of the sample to decide whether the rho, the true correlation between these two variables, is significant. Okay, so what we have available to us is a Pearson correlation coefficient table that's going to get us to give us a critical value. And if our R is bigger than that critical value in absolute value, because we're talking about the strength of it, then we will be able to say that there is enough evidence that the correlation coefficient rho is significant. So that's the conclusion we're trying to make. All right, so let's take a look at an example. Oh, well, first, let's look at what we would see on the Pearson correlation coefficient table. All right, what you're going to see is you're going to see n values. That's the number of pairs of data in the sample, basically the number of points you would have on your plot. All right. And then you're going to see critical values for the two commonly used levels of significance here, so 5% and 1%. So if we were trying to determine whether rho is significant, if you had 5 pairs of data and we're talking alpha equals 0.01, we would go here to the 5 pairs and use the 0.959 as our critical value. So if we have an R in absolute value that's bigger than 0.959, then we'd be able to say the correlation is significant. Otherwise, we can't. There is not enough evidence to conclude that the correlation coefficient is significant. So this is what the Pearson correlation coefficient critical value chart would look like, again in a bigger form. So again, with this number of pairs of our in our two samples here, from our two samples, and the levels of significance. So we would basically just figure out how many pairs we have, then we go to either the second or third column depending on what level of significance, and this would give us our critical value. Okay, so let's look at this in an example. So the one that we were looking at before. So Old Faithful, it's a new one. Old Faithful, located in Yellowstone National Park, is the world's most famous geyser. The duration of minutes of several of Old Faithful's eruptions and the times in minutes until the next eruption is shown. So basically, so this is two different, this is the same data split in two here. So you've got all the durations here and here. That's the duration of an eruption, and then the time until the next eruption. So what we're trying to see is there a correlation between how long an eruption is and then the time until the next eruption. So if you took all these 25 pairs of data, so the ones here and here, and you ran that whole number calculation, you would get an R of approximately 0.979. And what we want to know is that indicating a significant rho, a significant correlation between these two data sets? So we're going to test that using a 5% significance level. So, well, we would go to the Pearson correlation coefficient table, and we have n of 25, so we go down to the 25th entry here, or the n equals 25 entry, and at a critical value, so at a significance level of 0.05, our critical value would be 0.936. Okay, so obviously the absolute value of our R, so since it was 0.979, the absolute value had no effect. But so 0.979 is definitely bigger than 0.396. So we can say that the population coefficient correlation is significant. In other words, there is enough evidence at the 5% level of significance to conclude that there is a significant linear correlation between the duration of Old Faithful's eruptions and the time between eruptions. So not only did we find an R value, we were able to show that there is evidence that it indicates a significant linear correlation. But one thing we have to be aware of is the difference between correlation and causation. All right, just the mere fact that two things are correlated does not mean one is causing the other. So that's what we're saying in this first bullet point here. The fact that two variables are strongly correlated does not in itself imply a cause and effect relationship between the variables. It's a good reason to investigate whether there is, but you need more than just the correlation. So you should consider the following possibilities. So maybe there is. Maybe X does cause Y if two things are correlated. In other words, a direct cause and effect relationship between the variables. In the case we saw, the rising GDP of a country and its emissions probably has a lot to do with the increased industrial nature of the country and therefore the increased emissions. So there's good reason to believe in that cause and effect relationship. There could be a reverse cause and effect relationship between the variables. You may have looked at X as the explanatory and Y as the response, but maybe you're looking at it backwards. So if you found a correlation between the times people took umbrellas and the days in which it was raining, then you wouldn't want to say that people carrying umbrellas causes it to rain, or it's actually the other way around. It's the raining that's causing the carrying of umbrellas. So you may just have it backwards. The correlation isn't going to distinguish that. You would have to reason that. It's also possible that the relationship between the variables can be caused by a third variable or a combination of other variables. In fact, we have a name, so there are lurking variables that might not be in the study and may be having a profound effect on what's happening. So the fact that there could be things that you're not taking into account is often characterized in a famous statistical example in which people have found that there's a correlation between ice cream sales and murders. It's strange, but this is what they found. Now, does that mean that the higher the ice cream sales, that higher ice cream sales is causing the murders? No, it's unlikely that is the case. The reasoning seems to be, or people have postulated, is that there are rising ice cream sales when it's warm outside. So when it's hotter, people are out and there's more interaction with people that happens to end up causing an increase in the number of murders. So as gruesome as the example is, that's a famous statistical example for as a warning of not to directly try to establish a cause and effect relationship because of a correlation. And then it's also possible that the relationship between the two variables is simply a coincidence. So that is something that must be entertained as well. So you have to be careful. The most common phrase in this type of thing you'll hear from statisticians is correlation does not imply causation. Because things are correlated does not mean that one causes the other. It's just an indication that maybe you should look towards that.